Swayam Prabha. Digital India. Educated India.
Welcome back, students. Last lecture we were talking about the minor losses due to the contraction, and this week and in this lecture we are going to start the losses due to enlargement. So, what is sudden enlargement? A sudden enlargement in a pipe is something like this. You see, if there is a pipe which is going in a reservoir, for example, reservoir or any structure that is bigger than this pipe. So, going from one smaller pipe into a larger pipe, for example. So, this is enlargement. Okay. So, in that case what happens is the head loss can be simply given as V1 minus V2 whole square by 2G. Okay. In a sudden enlargement, it will be given as V1 minus V2 whole square by 2G. So, if there is point 1 here, 2 here and 3 here, the head loss can also be referred as KL into V1 square by 2G, where V1 is the velocity in the narrower tube, and what that KL is going to be, this KL will be again a ratio of A1 by A2, where A1 is the smaller. Okay. Suppose the second area is very large, all right. You see here. So, suppose this is very large. So, A1 by A2 is tending to 0, and therefore, the entire energy will be lost. This is just a matter of interpretation from the curve. So, best is to find the ratio of the areas of A1 and A2 and take the KL from here, put it here and multiply it by V1 square by 2G. You saw in the contraction it was V2 square by 2G, and in case of expansion it is V1 square by 2G. So, those velocities needs to be considered where the smaller pipes are there. So, the smaller pipe in case of contraction was at 2. So, we had K into V2 square by 2G. Here in case of enlargement, the smaller pipe is at 1. So, it is KL into V1 square by 2G. Okay. A KL will have a general formula as 1 minus A1 by A2 whole square. You can also use this equation for KL. Okay. You put A1 by A2 is equal to 0, that means KL will be 1. So, whole energy is going to be lost. I think it is better to remember in case of sudden enlargement, the KL is equal to 1 minus A1 by A2 whole square. Remember this one, it is easier, and of course this one. Okay. And in case of sudden contraction, KL was 0.5, if you remember. So, if you put this, we come back to the formula which we saw in the last page. You can also see head loss is going to be V1 minus V2 whole square by 2G, as we saw in the last slide here. Okay. This is also important. Now, you note that the drop in energy line is much larger than in case of the contraction. Of course, you will see that, because see, in most of the cases, in case of sudden contraction, the KL was 0.5, whereas in case of sudden expansion, KL is full 1. So, whole energy is going to be lost. So, in case of sudden expansion, the drop in the energy line would be very rapid. All right. and this is abrupt expansion. This is gradual expansion, this is abrupt. So see the sudden fall in the line. This is gradual, this is abrupt. Alright. So smaller head loss than in the case of an abrupt expansion is for the gradual expansion. Like we had the gradual contraction, we have something called gradual expansion. So head losses due to pipe enlargement may be greatly reduced by introducing gradual pipe transition known as diffusers. That was confusers and this was diffuser, something like this. In this case also we will have a formula for the head loss as Ke dash into V1 square minus V2 square by 2G, okay, and Ke can be taken from this table. I mean, you will be provided with those values if at all some question comes for the gradual pipe transition or gradual contraction or gradual expansion. But you have to remember for the scenarios like this. Okay. So now head loss due to gradual enlargement, again the same thing as we had in contraction, conical diffusers. In this also it will be HL is given as KL into V1 square minus V2 square by 2G, where you can, there are many experiments that have been done and you will find a different value of alpha, different value of KL based on different alpha, and more or less every value would be more or less similar. Okay. Now loss due to pipe entrance. So general formula for head loss at the entrance of the pipe is also expressed in terms of velocity head. So if there is an entrance, pipe entrance, okay, so the loss will be V square by 2G into K entrance. So for different configuration, this is the most common one that you will encounter. So you just need to remember this one, pipe entrance, if nothing is given you have to take the K entrance as 0.5. alright. In this case where the pipes are protruding inwards, Ke is going to be 1.0. So all the energy is going to loss. If there is a smooth curve like this, you saw in the third one here, it is going to be 0.04, but this is most important. So K entrance you have to remember, if nothing else is given, is 0.5, okay, and V square, of course V should be calculated here because this is a reservoir. In reservoir there would be very little velocity, okay, velocity should be here. Now the head loss at the entrance of the pipe, that is when the flow is leaving a tank. In this case it is the same thing, alright. So sharp edge, this is also entrance only, this is the one that we studied in the last slide. If it is well rounded, you saw that there was a value of 0.04, it is a much more good looking figure, but the message is the same. If it is well rounded, KL is 0.04, if it is slightly rounded it is 0.2, if it is embedded inside, you saw we had one figure where everything was inside, therefore there KL was equal to 1, but in this case it is 0.8. So more, this is nothing but pipe entrance. By default just take 0.5 if nothing else has been given. Now different pipe inlets, again the same thing, you see K inlet, K entrance. So these many equations you cannot remember, I mean these many values. So only the most common one, the one which I have been telling, try to remember those. So increasing loss coefficient has been demonstrated here like this. Another typical values for various amounts of rounding of the lip, You see, these are based on all the different experiments that people have done. So, these curves will be, now we have talked about entrance, we have talked about contraction, we have talked about expansion, now we have talked about entrance to the pipe. Now, what is the head loss at the exit of the pipe? Something like this, when the pipe is terminating in a reservoir. Okay, when the pipe is terminating in the reservoir, what is going to happen? Whole velocity, because the reservoir is so big, everything is going to be lost, right. So, if K exit is always going to be 1, remember that. You see, whatever this thing is, KL is always going to be 1.0, very easy to remember. And head loss is simply V square by 2G, where V is calculated at these points. Okay, don't try to calculate V here, because it will come to be 0 in the reservoir. The kinetic energy of the exiting fluid, that is velocity V1, is dissipated through viscous effect as stream of the fluid mixes with the fluid in the tank and eventually comes to rest. This is what exactly I have told you. Now, the head loss due to bends in the pipe, so many formulas are there. We say Kb into V square by 2G. Okay, velocity will remain the same, even the bend is there. So, we need to know Kb for different values of R by D. D is the diameter of the pipe and R is the radius of the curvature of the pipe. There are different values of Kb. Either you will be given these tables or given the values. Meter bends. So, due to there are head losses due to the pipe fitting, you see, different type, you will be provided with these values. Okay, everything will be K, all the minor losses of the form K into V square by 2G. Okay. So, if there is a closed valve, there is open valve, see there are losses of the order of 10.0 if the valve is fully rotary valve, it is fully open. So, the loss coefficients has been summarized here for elbows, bends and T's. You see 0.3, 0.1.5, 0.2, 0.7, 0.2, 1.5, 0.2, 0.9, 1, 2. So, this is a table again for pipe components. So, for the examination and assignment purpose you can look back you can keep the tables with yourself, but in exams these values will mostly be provided. Only those values which are very common, like the K entrance, K exit, sudden contraction, sudden expansion and things like that, that won't be provided. Those values will not be provided and you are expected to know this, the formulas. Okay. So, important message is that minor losses is K into V square by 2G. And K can be obtained from tables or charts. Okay. So, this is a table of minor loss coefficients. I said this is a summary, do not have to worry about it. This is when you go and start working in a company where this pipe losses are relevant, then you can make the use of this type of charts and table for quick reference. All right. So, minor loss calculation using equivalent pipe length. So, equivalent pipe length can be written as KL into D by F, where LE is the equivalent pipe length that we are going to calculate, D is the diameter of the pipe, K1 is the loss coefficient for any fitting valve and F is the Darcy Webash coefficient. For example, there are several pipes connected in either series or parallel or a combination of those, and somebody asks you to calculate the equivalent pipe length. If there was one single pipe with equivalent pipe, the diameter with equivalent pipe diameter, what would be the effective pipe length? So, you can use this formula. Now, let us solve a question, so that gives us more confidence. These questions is about major and minor losses mainly, and it says that a pipeline of 60 centimeter in diameter takes off from a reservoir whose water surface elevation is 150 meter above the datum. Okay. The pipe is 5000 meter long and is laid completely at the datum level. In the last 1200 meter of the pipe, water is withdrawn by a series of pipes at uniform rate of 0.088 per 300 meter. Find the pressure at the end of the pipeline. Assume F is equal to 0.02 and the pipe to have a dead end. Okay. So, if you understand this question, so I am going to solve this. So, first an expression for the head loss in pipe having a uniform withdrawal of Q star meter cube per second per meter length is derived, because it says the water is withdrawn by a series of pipes at a uniform rate. All right. So, to be able to do that, we consider a section at a distance x from the start of the uniform withdrawal. Okay. So, this is a pipe, this diameter is d and we have Q naught, and from here we assume a distance x, okay, and this distance is L naught. All right, and the withdrawal is uniform, that is Q star. So, discharge is going at x will be Q naught minus Q star into x, right. So, in a small distance dx, so at x we assume small distance dx here, the head loss is going to be FLV square by 2GD, right, or instead of V we write Q, correct. So, we can write F Q naught minus Q star x whole square and so 2g into pi by 4 whole square into d to the power 5. All right. So, after, so I will take this here now. So, just writing DHF will be just writing 8f divided by pi square g d to the power 5 into q minus q star x whole square dx. All right. So, HF is going to be integral of DHF, and from where 0 to L naught. This is going to be from 0 to L naught. Okay, so now we calculate. So HF comes to be 8F divided by 3 pi square g d to the power 5 into 1 by q star q naught cube minus q naught minus q star L naught whole cube. All right. So this is the a general head loss for the continuous withdrawal that we have found out. So in present problem, Q naught is 1200 by 300 into 0.088. All right. So we have 0.352 meter cube per second, and this Q star is 0.088 by 300, that is 2.933 into 10 to the power minus 4 meter cube per second per meter, and L naught has been given as 1200 meter. All right. So apart from that, if we say HL is equal to total head lost, okay, what is the total head loss? So head lost in first 5000 meter with discharge Q naught is equal to 0.352 meter cube per second plus head lost in last 1200 with uniform withdrawal. So total head loss is going to be the head lost in first 3800 meter with discharge Q naught, that is going to be the major head loss, right? And the second one was we used differential equation, and that is what we wrote HF2, okay, here HF. So total HL will be HF1 plus HF2, and what is HF1? It's the major loss, right? And that is going to be 0.02, that is already given, into the length was 3800 into 0.352 whole square, because that is the velocity, 2 into 9.81 into pi by 4 whole square into 0.6 to the power 5, and this comes on calculation as 10 meter. What is the HF2? Is the last 1200 meters where we have derived that equation, which was 8F. This was what we derived, 3 pi square g d to the power 5 into 1 by q star into q naught cube minus q naught minus q star L naught whole cube. And if you solve this with the appropriate values of f is 0.02 and other things, you will get HF2 as 1.053 meter. Now the question is, what is the residual head at the dead end? So this is going to be the residual head at the other end. All right. One 138.947 meter. Okay. So these are lengthy questions, but the idea of covering these is that you are able to solve any type of problem after learning this course. Of course, the assignment will have simpler problems because it will be mostly objective type or fill in the blanks. So there will be small problems rather than such big and complicated problems. But this is a nice practice and will expose you to all type of problems that you can encounter in pipe flow. Now something about energy and hydraulic grade line, you see. So unless the local effect are of particular interest, the changes in EGL and HGL are often shown as abrupt changes even though the loss occurs over some distance, you see. Okay. So in the figure shown below, two new cast iron pipes are in series, length of each pipe is given and level at A is also given. All right. Now we have to find the water level at B. A very simple and good question. Okay. So see, whatever be the difference between the levels at A and minus B, this ZA minus ZB should be equal to the HF, that is the head loss between point A and point B. All right. Okay, and now this HF should be the sum of energy loss, I mean the losses. Now can you think where these losses will occur? There will be a loss at the entrance here, right? There will be a loss here, okay, due to contraction, and there will be a loss due to exit. Apart from that, these are the three minor losses. There will be one loss, major loss M1 here, and there will be loss M2 here due to the flow in the sections of the pipe, long sections of the pipe. All right, good. So to solve that, we will take the help of white screen again. So solution number 10, ZA minus ZB is equal to HF, and this total HF or HL will be HF1 plus HF2 plus H entrance plus HC plus H exit. The three minor losses and the two major losses. F1 means major loss in pipe 1, major loss in pipe 2. Okay. So we can simply write the formula first. F1 L1 by D1 into V1 square by 2G plus F2 L2 by D2 into V2 square by 2G plus K entrance V1 square by 2G plus Kc into V2 square by 2G plus K exit into V2 square by 2G. This is an important formula that, and now we need to find out the flow properties in pipe 1 and 2. So simply pipe 1, they will be discharged by area 1. Discharge is given 0.5 and this is the length and diameter, everything is given. So it will come 1.77 meters per second, whereas V2 will come out to be Q by A2. 0.5 diameters are different, so pi by 4 into 0.4 whole square, and this will come to be 3.98 meters per second. All right. So if we know our V1, we know RE1, V1 D1 by nu, and you put the value of velocity d and mu, you will get 8.1 into 10 to the power 5. Similarly, here RE2 will come out to be V2 D2 by, you would be wondering why we need to calculate Reynolds number and those parameters. The reason is we want to calculate the major head loss, and major head loss will depend upon F. F is the friction factor which will depend upon Reynolds number and epsilon by D. Alright. So, this come out to be 1.22 into 10 to the power 6. Okay. So, we have calculated RE1, we have calculated RE2. Here epsilon by D1 will be 0.26 divided by 600, and here epsilon by D2 is going to be, so this comes out to be actually 0.00043, and this one comes out to be 0.00065. So, we know RE1, here we know epsilon by D1, here we know RE2, here we know epsilon by D2. So, we can actually use the Haaland equation or the Moody's chart and find out F1. F1 will, if you look at the Moody's chart or find the Haaland equation, use the Haaland equation, it will come 0.017, and this F2 is going to come to be 0.018. Alright. So, now it is just the matter of putting everything together. I am going to use this slot. So, HF, so we know everything, 0.017 into 300 by 0.6 into 1.77 square by 2g plus 0.018 into length is 300 only by 0.4 into V2 square is 3.98 whole square by 2g. These two are major losses plus minor losses. The entrance was the 0.5 into 1.77 square by 2g, and this 0.27 is given to us, or we can look up at the table, 3.98 whole square by 2g. The last one is exit, so whole energy is going to be lost, so 3.98 whole square by 2g. So, if you calculate, in the end the total loss is going to be 13.36 meter. So, let me rub something here. Okay. So, the final solution, the head loss is going to be 13.36 meter, and therefore ZA minus ZB is going to be 80 minus 13.36. Alright, I think we should not make it so much cluttered, but now you understand the process. We calculated the major losses, we calculated the minor losses, and we calculated the total thing, and here we get the level at ZA as 80 minus 13.36 as 66.64 meter. Okay, this was the elevation. Good. So, I think with this I will end today's lecture and continue in another lecture when we meet next. Thank you so much for listening. Have a good day.